Okay, they did get through the 4.5 and 4.6, or 5.5 and 5.6 assignments. I've got some comments, I'll send them out, but I'm kind of waiting for everybody to get those in, okay? Still a couple of people that I haven't seen them from. Most people I have. So I'll give that another day or so and I'll send that out. But the one comment I'll make is, it's not unusual, but most of you are doing real well with the integration. Okay. And it goes back to a lot of things. Goes back to preparation, and the preparation goes all the way back to middle school. And there are things you gotta know that you didn't learn at the time when you were supposed to learn it because nobody taught it. Or if they might have talked about them, but you were never really responsible for knowing. Unfortunately, there's a lot of that in our education system. A lot of it goes back to COVID, but that was happening before COVID. COVID just made it worse. And now AI is making it even worse because people are relying on AI rather than their brains, and it's dumbing everybody down, which is a dangerous thing all the way around. Okay, it's dangerous for society. It's dangerous for our economic future. So all that is your responsibility. There are 6 of you. I want you to fix it all for everybody. Got it? Okay, no, but I want you to make some steps. So I'm going to be sending out some progressive problems that are related to integration and shapes and how you analyze them and so forth. Okay? Start with easy stuff like how far do you have to go up from the point X, Y to get to the paraboloid 9 minus x squared minus y squared. Okay? Stuff like that. You need to focus on that. And you need to understand how to set up these inequalities. And then once you've set up the inequalities, how do you go to the interval? What does it mean? What are you really doing? You're really going to need that in about a week or two. Okay? It's optional. You don't have to do it. I'm going to send it out, but I would like you to write it out and bring it to me on a piece of paper. Okay? It's going to come in piecemeal. I know people. Okay? And stuff that comes in piecemeal is very difficult for me to keep track of in Adobe. Okay? It's not that difficult. It's possible, but it's distracting. Okay? I can handle it with the homework. I want paper. And if you want to keep your work, make a copy. Eventually, I might be able to sort and copy it, but the whole copy situation is a little weird right now. Okay. Now, what we're getting into in chapter 6 is the vector calculus. Okay. It's very important in many fields. My grandson was in last weekend. Remember that thing about the similar triangles last time? I asked him how many times had he seen similar triangles at Tech. Said in his engineering courses, never. In his math courses, all the time. Okay? It's just something he learned in middle school and developed. As we went on. I don't think he took any of my math courses just because he's doing it in his junior and senior year. He took a physics. Not just the physics. I really wanted to get him into this course. But he got into Tech. They gave him a good course. Good courses are good. Okay. So we're getting into vector calculus. We talked last week about vector fields. It's kind of a mistake. I didn't get an assignment of vector fields posted. But I'm not going to talk too much about vector fields right now, except that how aware are you of the Artemis thing that's out there around the moon right now? Okay. If you look in chapter 6.1, very quickly you see a vector field of the Earth and the moon. Okay. It's a vector field that's very easy to work out, except that everything's moving. So it's a moving, it's a constantly changing vector field. Very interesting. I did a lot with that one year when they were sent up. I forget what the name of the mission was, but they sent up a satellite, went way out past the moon, came back, orbited a few times. And, they were posting the telemetry. So I could figure out every little while, I'd take some data and I could figure out where it was, how close it was to the moon, how fast its energy is changing, stuff like that. Nobody wanted to pick up on it. Nobody's interested. It's fascinating stuff. Okay. So there are going to be 3 sections due today. You want to for sure get section 1 done by Thursday, okay? Maybe start into section 2 and 3. One of the big deals, and I'm going to kind of cut close to the end here because I want you to see where all this is heading, okay? Or at least you get some idea. And I've already talked about it. Well, now, actually, first I've got to talk about line integrals. So line integrals, that's Greek. I wrote that in Greek. Nobody knows how to read that anymore. Okay. Line integrals. Line integrals was important enough that I wrote it halfway carefully in cursive. Okay. Idea is, well, you already know about line integrals. You've done line integrals. You've done for arc length integrals, right? And so it's like ouch. Got a curve. See, it's described by parametric equations, let's say. So typically, we'll describe it by an R of t vector, which is a vector from the origin out to a graph point. So we could have an R of t here. An R of t plus delta t here. All the stuff that we did in chapter whatever. Chapter 2, maybe. Okay. Just to kind of review what you should remember, we have a delta R. Between R of t and R of t plus delta t. And R prime of t, its limit as delta t approaches 0 of delta R over delta t. And we can see that as we use a shorter and shorter delta t, that this R of t plus delta t vector, it just traces the curve here. It's going to go a little bit lower, right? It's going to get a little bit closer to the origin than it was here. And this delta R vector is going to point down just a little more. It's going to continue pointing downward as the R of t plus delta t vector slides along here until it's tangent to the curve. So that's a limit. It's been described in your text. I've talked about it, but I just want to refresh your memory because it's really kind of an important thing to understand. Okay. So you got a curve C defined by R of t equals x of ti plus y of tj plus z of tk on some interval, some t interval, a less than or equal to t less than or equal to b. So right here is I'm just searching for notation here. I'll just call this P sub A, point corresponding to t equals A. And P sub B, the point corresponding to t equals B. Okay. Now on a typical interval, okay, well, we partition. The interval AB. Partition always kind of looks the same. A is equal to T naught, B is equal to Tn, n is the number of intervals into which you partition this thing. And if you're trying to watch it on the screen, you're not seeing it. Everything here is pretty straightforward, but once you be able to see it rather than have to conjecture it. Okay, there's our partition. So the typical partition we'll just take to be, this one here. We're going to take the interval of the partition. Okay, so let's take this interval over here and enlarge it a bit. Kind of going in this direction. And it goes from here. This vector here is vector r of ti minus r of t sub I minus 1. Okay. That's approximately equal to r prime of ti star delta t sub I, where ti star is the sample point between ti minus 1 and ti. I mean, you got to evaluate things at some point. You can't evaluate them at all points here. You'd have to do an integral to do that. Okay? Evaluate whatever you're trying to evaluate at some sample point, some arbitrary point. And where you put your sample point makes a little bit of difference. But as the intervals shrink down to zero, shrink down to length zero, you have less and less wiggle room as to where you put the sample point, right? So you're putting a sample point randomly in an interval that shrinks to zero. Pretty soon, you've got to squeeze down to a point, okay? You got to kind of understand that. So do we understand this so far? I mean, this is R of Ti minus R of Ti minus 1, just like this little vector here is R of T plus delta T minus R of T. That's our delta R, right? Understand those things. Okay, well, that's our delta Ri vector. Our delta R on the ith interval. The vector we get like this if we subtract this vector from this vector. Subtract this vector from this vector, you get something that when you add it to this vector, you get this vector. What do you add to this vector to get this vector? This, which is the difference of the two vectors. Really, really lock into that. If you don't completely understand it, and it's not atypical, a lot of people still be a little foggy about that at this point, of course. If you are, you're probably among at least a significant minority, if not a majority. Okay, a lot of people do understand it. But okay, well, we got this vector. Now, if we want to know the arc length of this thing, we just add up all the arc lengths of these vectors, right? Okay, we can write this vector out a little more explicitly. I'll let you make the connection. Well, no. It equals R prime of Ti star delta T sub I. Since R of T is X of Ti plus Y of Tj plus Z of Tk, then R prime is going to be X prime I plus Y prime J plus Z prime K. Evaluated at our sample point T sub I star. Tells us how fast we're moving in the X direction, how fast we're moving in the Y direction, how fast we're moving in the Z direction. If you think of this as time, and then it's times our delta T sub I. The distance It'll be written this way, just how fast we're moving in each direction. Square it, take the square root. Yeah, add up the squares, take the squares, Pythagorean theorem. And this is often written I'm kind of suppressing the I, but remember, all these are evaluated for a given increment at the sample point Ti star. Okay. When you take the limit, though, you get something like dx squared, dx dt squared, dy dt quantity squared, dz dt quantity squared. It's like you got a dt squared in the denominator, cancel out the delta t there. Okay. You'll see it in that form. That's not really what happens, but it's kind of like what happens. It follows if the arc distance, maybe I can keep this up here so you can still see it. I'll start writing on the other side over there. Um, got a block that I use to support this thing. I just bit in the dust, it's on the floor. Okay, we'll leave that there where everybody can kind of look at it. Okay. Um, okay. Now, the arc distance is just the sum of these distances, right? The approximate arc distance is the sum of the magnitudes of these little r vectors that make up these increments, okay? Or that make up the approximate arc distance in each increment. If your density is sigma of x, y, z, then the mass of the ith increment is sigma at x of ti star, y of ti star, z of ti star. In other words, you're taking the density at some sample point within whichever increment you're looking at, okay? And you're multiplying it by the length of the increment. Length of the increment is how fast you're moving on the increment times the time. If you regard t as time, whatever the parameter is, that's how it works. Let's call that delta m sub I. Total mass is approximately the sum of your m sub i's as your delta t sub i's all shrink to zero. That approaches the integral from a to b of your density function times the magnitude of your ri prime of t times dt. If you want the moment of this function about the z-axis, you multiply this for each increment by its distance from the z-axis, which is x squared plus y squared. Okay? Not going to get into that. That's in section that I'm starting to see in my email. Okay? If you want the moment of inertia, you multiply this by x squared plus y squared, moment of inertia about the z-axis. I think I've got enough parentheses in there. That's the idea of the line integral. And you can use the line integral to calculate moments, to calculate mass, to calculate other things. Okay? Now you can also, you got your delta r sub I increment. Just sitting here waiting to do something with it. Bring this board back in a minute. But let's say you got your delta r sub I, okay? So here's your delta r sub I. I'll remind you that's equal to magnitude of Ri prime delta T sub I, okay? Again, how fast by how long you're moving. And Ri prime, right again, is just square root of xi prime plus y squared plus y prime squared plus zi prime squared. That's how you practically apply it. You got to sort that out. You do a couple examples. It's not particularly difficult. I remember having to think a little hard about it when I was learning to do it. It didn't come full blown into my intuition. I had to work with it for a while. You will too, if you haven't already. Okay, now let's just say you got a vector field. Okay. And we got some vector. F of R of Ti star, okay? Why do I have this expression? This means at the time Ti star, R of Ti star gives you a point within this increment, okay? And that vector function has a value at that point. So that you calculate F dot T at this point, okay? For T is the direction of motion along the curve, okay? So that this delta R by is in the approximate direction of the tangent to the curve. I'll show that again. Just see, within the curve, here's our delta R sub I increment. Here it is in our curve. Go to some partition, and you've got this vector field. What color did I make the vector field? And I made it white, that's okay. So we've got here's our vector field. And let's say here's our unit tangent vector. And here's the actual increment. If we do F dot T, we get the component of F in the direction of motion. And we can show that here. I misuse the word increment there, but I think it's clear what I mean. Component of F in the direction of the increment. Actually, it's the delta R vector. Okay. So here's how it looks in the context of the entire curve. So what you're seeing here is just isolating that to that one little section of the curve. What are you trying to see? Get it? Okay. Okay. So does that make sense? First of all, F dot T is just a scalar quantity. Dot product is a scalar quantity. So it's really no different than like a density, but it I mean, as far as the way it's treated. But for example, if F is a force, this is the force in the direction of motion. Okay. If you multiply the force in the direction of motion by the distance through which it travels, you get the work. Okay. Force or displacement times work or work. If this is an electrical field and you have a charged particle moving through the electric field, you multiply the electric field by the charge, and that's a force, and you do the same thing. If it's a magnetic field, those of you familiar with them, you got to integrate the component of force perpendicular to motion. Okay. Because a magnetic field exerts a force on a charge. If the motion of the charge is in this direction and the magnetic field's in this direction, you got to do a cross product and you get something perpendicular. Okay. So I'm not going to detail that. I just mentioned it because that's kind of where physics courses are at this point. Okay. Gives you an outline. You have examples in section 2. Okay, but it gives you an idea what a line integral does. Okay. Now, this is where it gets neat. Normally, if you do line integral, you got to go through all the mechanics of setting this up and doing the integration. If you know your R vector, you can calculate the magnitude of your R prime vector. And if you know your density vector, function of X, Y, and Z, R is a function of X, Y, and Z, okay? You could actually call this sigma at R of T. Because R of T is can be identified as a point on the curve. For every T, the end of the R of T vector is the point on the curve. And as the R of T vector maneuvers around, the end of the vector maneuvers around, traces out the curve. Okay, so that's a little bit of an abusive notation, but you can kind of think of it that way. And to learn this, you got to go through the details of setting these things up, but you always want to have the overview of what it's telling you so that it means something. Rather than just when I see this, I calculate this, but what the heck's it? Okay. And you're at that stage when you start, but you want to get to the stage of knowing what it means so you can hang the process on some meaning and remember it. And at least know 5 years in the future, when you have something that's relevant to this thing, you at least have the concept and can redevelop if you need it. And knowing what to integrate, how to integrate it isn't all that important, except you still have to jump through that hoop. Okay. I don't think any engineer in the country has done an integration in the last 50 years. They use machinery. But the best ones know at least how to approximate the interval. Okay. And if it's a straightforward substitution stuff, if they picked it up, it'll keep reminding. Okay. Let them lose track. Like my grandson said, he hadn't seen a similar triangle in any engineering course. But he saw it in all his math courses. The whole idea of proportionality and so forth. Okay, now where it gets really neat, I'm just going to kind of cut to the big stuff here. If your vector field is a gradient, okay, so here's what we're going to do. We're going to break up the three groups. Yes. Yes. You're going to share your research questions. The revelation is that the integral of the gradient, well, first place, if then isn't appropriate here. Suppose f of x by z is a gradient. Easy to show that the integral of the gradient, the line integral of the gradient, is just the value of f of b minus the value f of b minus the value f of a. That's kind of like an antiderivative, isn't it? It's like this gradient function, which might be a function of 2 or 3 variables or more. Okay. Like this function here is kind of analysis. It's just a simple function, x squared, integrate x squared from a to b. Okay. X cubed over 3, evaluate it. Okay. If f is a gradient function, then the function of which it is a gradient tells you immediately what the integral is, and the path doesn't matter. Okay. Or any path. And I'll say from R of A to R of B, because remember, we're still talking in terms of a vector function that defines your curve, right? It's just like, okay, here's R. Here's R of B. And here's a curve that goes from R of A to R of B. If you're going to integrate that curve, you're going to set it up from the foundation. You're going to start by partitioning the interval, say the t interval, from A to B. Okay? Just like we've talked about. Then you're going to take a limit, and whatever it is you're wanting to evaluate, whatever gradient function you're wanting to evaluate, the result depends only on the value of the potential function here and the value of the potential function here. Now, I did just throw out the word potential function. Del F is a gradient function. F is the scalar potential function. In gravitation, physical gravitation, you have a potential energy function. The Earth, the Moon, have a potential energy function based on forces exerted by two objects. Okay? What's the potential function? Tells you how much work you got to do per unit of mass to get from one point to another. In electricity, you have electric field, which is a gradient of the potential function. The electric potential function is also called the voltage function. Okay? Now, whether you are conversant with those things or not depends on where you are in your physics, but that's what we have. Okay? Very, very relevant to mechanical, electromagnetic, most engineering. Okay? And you also have analogs to this in like systems engineering, data science engineering, okay, which is really hairy. All right. Now, the big deal about this, one of the big deals, both things are a big deal, but one of the big deals is it doesn't matter what curve you use to go from here to here. Okay. I could use this curve and I'd get the same thing. Also, if I combine these two curves by going from here to here along the first curve, and then continuing along the second curve back to my original point, well, the line integral across this curve as I go from here to here is equal to the line integral of the other curve as I go from here to here. But of course, if I go from here to here along the first curve, my initial to final point, let's say along the first curve, then I go from the final point back to the initial along the second curve, my integral along the second curve is the negative of what it would be if I went from the initial point to the final point along it. Which means if the integral along the first curve is 10, then the integral along the second curve from the initial point to the final point would be 10. But the integral of the second curve from the final point to the initial point would be negative 10, which means if I go around the whole loop, I get 10 and negative 10, 0. Okay? So So, okay, I have an integral over C, where C is a curve, okay? And I've got a circle on that integral indicating a complete loop, okay? Means a closed curve. The integral of this same thing that I don't have room to write here around any closed curve is zero. Path independence means is equivalent to saying the integral on any closed curve is zero. Okay? Your book will explain that in more words and better words, but without all the body English. Okay? Make sense? Very important principle. If this is the case, if F is conservative, i.e. path independent, physics, you say the gravitational field is conservative because it is path independent. If I use the analogy in physics, if I lift a concrete block from here to here, okay, and then lower it again, the work done by the gravitational field on that block is zero. That work done is zero. Gravitational field does negative work when I raise it here because the field's down and my motion is up, right? Which increases my potential energy, if you know about that. And then I lower it back down. Gravity does positive work, equal and opposite to the negative work it did going up. Because the gravitational force doesn't give a hoot in what direction you are moving. It's going to exert the force in the direction toward the center of gravitational object, center of the Earth in this vicinity. Okay? So any closed path you want to take, send your drone out exploring the world. By the time it gets back to you, gravity will have done zero work on it. Sometimes it's doing positive work, sometimes doing negative work, but the net work is the work it does going up minus the work it does work it does going up, which is negative, plus the work going down, which is positive. They cancel out. Okay? This is a little intuitive. What do we mean by conservative? In physics, you got conservation of energy, conservation of momentum, okay? Conservation of charge, conservation of this, that, and the other thing. And conservation law is extremely important. Conservation of angular momentum, it's a little hard to understand. Okay. Get the idea? This is an overview. I don't have time to go through all the details. But we got a little more time, so we'll go through a few more details. Okay. So let's just work out an example. Oh yeah, there is one more thing. We'll get that in the example. I tell you one more thing. Now, we haven't gotten to curl in the book, but I've defined it as del cross F, cross product of the del operator with whatever vector function, right? Okay. F is conservative if and only if del cross F is the zero vector. Actually, I'm going to prove that. F is conservative if and only if F is a gradient of F for some scalar function, I abbreviated function, I put the word potential in parentheses to remind you that we do call that a potential function for this field. Okay. Gravitational potential energy function is the potential function for the gravitational field, which is the gradient of the potential function. Okay. Uh, it's the gradient of fxi plus fyj plus fzk. I didn't want to put a line there. I want to put a sorry, that is what the gradient is. Okay. Everybody should understand that completely. It's a simple, very simple calculation. Well, then it's the del operator, which you know, course respect to xi, course respect to yj, course respect to zk, cross product with this. Well, among other things, let's just take the partial respect to I, cross it with each of these. You can use a determinate definition, that's fine. Let's see what's really going on. If I do the partial with respect to xi crossed with fxi, I cross I is zero, so we don't get anything, right? Cross I with j, we get k. I cross j is k. So we're doing the partial of fy with respect to x times k. So we get fyx from partial respect to x of I crossed with partial respect to yj. Partial respect to xi crossed with partial cross with f z k, I cross k is negative j. We're going to get a negative x derivative of the fz x, okay? And then we can do the partials of y with respect, partial with respect to y times the j vector times the I vector and times the z vector. Well, let's do that. Partial with respect to y of fx. That's going to be what we get when we cross the j with I. J cross I is negative k, right? So from the partial with respect to yj in the fxi, we get negative f xy. Well, what is fyx minus fxy? Show me with your fingers. It's zero because the order of your partial derivatives doesn't matter. That's fyx minus fyx. Okay? Well, you keep doing this. There are three other cross products you could do without doing the determinant thing. And you find that everything gives you zero. So we've proved that if f is conservative, cross product is zero. We're not going to prove the converse, that if the cross product is zero, that f is conservative, but it's not hard to prove. We just don't want to take the time. Okay? A little more subtle. So all that stuff implies del cross f equals zero. But of course, if you want to do I, j, k, r's with respect to x, r's with respect to y, r's with respect to z, fx, fy, fz, and I say if, you should do this. I'm not going to do it for you. It's simple. You should do it and see it. Okay? And this is called cross partials add up to zero. Now, your book tells you that the cross partials add up to zero before it ever mentions a curl. Okay? Because actually the formal way your book develops it kind of makes that a good idea. I'm skipping it. When you see it, if you've worked this out, you'll know exactly what you're seeing and you'll recognize it and you'll be able to use it. And that's enough to make me very happy. Okay? It's enough to make you happy. Unless you're going to be a theoretical mathematician, there's a subtlety there that you can afford to miss. Okay? Given the way weather impacted the semester and everything else, we can sacrifice that little subtlety. Fair enough? And I know you just should not be bothered with it too. I'm not sure I wanted to think about it at the time. And I'm not sure that it was developed in Thomas, third edition, in the opposite way, but doesn't matter. Okay. It's been pushing 60 years. Okay. Now let's talk about how you might derive a scalar potential. How many have had differential equations? Most of you? Yeah. It's going to remind you of something you do in differential equations, at least if you learned it in differential. Let's just cheat and start with some function f of x, y. Let's just make it a simple function. Let's make it x squared y cubed plus y squared. Okay. It's two dimensions. The gradient of f is going to be 2x y cubed I plus 3x squared y squared plus 2y j. If I did my derivatives correctly, this is conservative function, a conservative field. Now let's say you were given this and you weren't given the form of f of xy. It's gone. I don't know what the heck f of xy was. You think I'm going to remember all the way back? So you probably wrote it down, but forget it for the moment. Okay, how do we get that? Well, two x y cubed is a partial of f with respect to x, right? So f equals 2xy cubed dx. The integral of 2xy cubed dx equals x squared y cubed, but not just that. You got an integration constant. Which I'll call h of y because y is constant when you're integrating with respect to x, right? In other words, any y function that doesn't involve x directly isn't going to appear here. Okay. And maybe plus a capital C, which is a scalar constant. But of course, C could also be subsumed under h of y. Okay. Also, three x squared y squared plus 2y is a partial of f with respect to y. We know that. If this is a gradient of some function f, then this thing is fx, this thing is fy. So we integrate this. So f equals x squared y cubed plus y squared. Okay. Plus, we'll call it a k of x, some function of x. That makes sense? Well, these functions have to be the same. This has to be the same as this. I could also put plus a c out here, but I've already got it up here, so it's going. Well, can you tell me what h of y has to be? It has to be y squared. Can you tell me what k of x has to be? Well, we don't need it because I already got x squared y cubed. Okay? So there it is, and I believe that's the function I started with. Can't even see it there anymore. Better be. Fairly simple example. Okay, that halfway makes sense? Does that look like something you saw in differential equation, maybe an exact equation or something like that? Okay. Okay. Um, so do you understand everything you saw here so far? Okay, I jotted down a few notes because I'm pretty worthless today and I don't want to forget anything important, although we still have Thursday to refine what we've done. So I'm going to look at those notes, the details, but okay. Okay. When you do line integrals, there's one other really important line integral thing that you got to know. I'll just start a new picture. Pretty soon, you're going to see curves or surfaces that are closed. Okay. So let's just take this right now as a closed curve because surfaces are a little more involved. Okay. And what I want to talk about is you got a vector field, and instead of integrating the tangential, I'm not going to draw all these partitions, although I'm kind of getting into it. So here's our typical partition. We still got our well, there's our delta R sub I. Mixing up my notations. This vector is Ri prime. If Ti stops, there's chalks being uncooperative. Probably because I dampened the screen. Um,
That's interesting.
so we have this increment. And what we want to integrate this time is the normal component of this thing. So we're going to have our normal vector perpendicular to our R vector. So it's going to look kind of like this. A little careless with notation here, but I want you to get the idea. Then our normal component of this function, as you probably know, is this, where this is our f vector, f of r ti star. This is our normal vector. More notation than you want to look at right now. We dot f with a unit normal vector and multiplied by the unit normal vector. Okay, and I've written the unit normal vector as any normal vector divided by its own magnitude. If it's written as small n unit vector, it's just f dot n times n. Okay. And the flux is Fn times magnitude of your delta R. Now, flux through a line curve isn't as important as flux through a surface. If it's flux through a surface, the normal vector is the normal to the tangent plane at that point, and you have an area increment on the surface. Okay, but we haven't talked about surface integrals yet. That'll come maybe late next week, maybe the following week. There are 9 sections in the chapter. We're going to do 3 of them each week. That'll give us a little bit of time for review, pull things together. Okay? Okay, so get on top of it. Got questions, please let me know.